Engineers with the knowledge and skills to create a functional drawing, that means engineering drawing as per the function of the part, selecting the tolerance value for each dimension and optimizing them for the cost and function are in demand with the design industries. Selecting the tolerance value is not a one-step process. It involves multiple knowledge areas to finalize dimension and tolerances. For example, engineers need to have knowledge of how to select general tolerances as per ISO 286. But that is only first step. We should also have knowledge of functional dimensioning and tolerancing with the engineering fits and GD&T as per ASME Y14.5 and ISO 1101 standards. Once we provide functional dimensioning, next critical phase is to optimize this tolerancing and dimensional chain, which means how we dimension the part in the drawing. And that's where tolerance stack-up analysis is going to help us. Tolerance stack-up analysis should be connected with manufacturing variations to make it more realistic. My name is Kevin Kutto, and in this video I am going to explain fundamentals of tolerance stack-up analysis and why tolerance stack-up analysis is so critical. So stay tuned till end. Do subscribe, like and share. It will help me to reach more design engineers in need. So let's begin with this fundamental question. What is tolerance stack-up analysis? A tolerance stack-up analysis is a calculation. And what we calculate here? We calculate maximum or minimum distance. And this maximum or minimum distance can be clearance or interference. And this distance will be between two features on same part or different parts in assembly. So here are two examples. In the first example, we have a groove on the part which is not dimensioned. And we want to find out what is the maximum and minimum distance or width of this groove. Now obviously this width will be the result of variations of all the dimensions which are concerning. And if we find those dimensions and how those dimensions are going to vary, we can easily predict what will be the maximum and minimum variation into the groove size. And that's where we are going to use tolerance stack-up analysis. We have one example of assembly also. In this assembly we have container and there are multiple parts which are stacked together. And our aim is to find out the clearance here. The reason why we have to find out this clearance is because we want to fit another box here. Now this clearance will be derived by the variations of all the dimensions of all other parts which are going to affect this clearance. And with the help of tolerance stack-up analysis, we can easily find out what is the maximum and minimum variation which is going to happen in this clearance. And that way we'll conclude whether we can fit in more box here or no. Both of these examples are example of clearances, but we can have example of interference also. This is the example where instead of clearance we have an interference which is important. So we have two snaps here and then there is a part which is assembled in this direction. So when we try to assemble in this direction, it is going to deflect these plastic snaps and it is going to fit into this. Now it's very important that we have positive interference here between snap and these parts. If there is a clearance, then this part will come out. Now somebody will say, why can't we provide more interference so that this part will not come out? But we have a trade-off here, because when we try to insert this part has to deflect the snap. And if the interference is more, that means it has to deflect snaps more, and that is going to increase the force requirement to insert this part into the snaps. So there is a trade-off here. We want to find out the sweet spot where we need the exact amount of interference which will meet both force requirement as well as it will prevent part from coming out. So this is the example where we have interference as a design requirement, and that also we can calculate with the help of tolerance stack-up analysis. Now let's understand what questions do tolerance stack-up analysis answer. Now I can talk on this topic for next 1 hour. There are so many advantages of tolerance stack-up analysis, but we are just going to understand few of them which are very critical. The first one is, will the parts in assembly assemble with each other readily or not? Because all the parts will have variations. There are so many dimensions and tolerances which are going to play the role. And if they go in worst case, then what is going to happen into the assembly? We can easily find it out with the help of tolerance stack-up analysis. Are drawings complete with all necessary dimension and tolerances or not? If I give the same part to create a drawing to multiple engineers, I'm sure that they will dimension it in different ways and they will provide different tolerances. Now, which one is correct one? We can easily find it out with the help of stack-up analysis. When you start doing stack-up analysis, you can easily find out if you have covered all the dimensions which are very important or not, and whether your tolerances are optimal or not. Have we understood product design fully, identified the problem in paper stage, and looked into the way to improve the design? What do we mean by this? We do stack up analysis in paper stage, that means in design state, when our parts or tool is not ready. And that's where we can easily check whether it is meeting the function or not. We can easily check whether we are meeting clearance or interference requirements or not. If you're not meeting, we can easily modify the design and we can make sure that our design is robust. It is also going to help us to identify the relationship of contributing dimensions and the output, which will eventually help us to understand our design in depth. Will the dimensioning and tolerancing scheme used on the part allows too much variation at assembly? What does it mean? Now imagine we have part like this, okay? So I am going to drive part something like this. And this part can be dimensioned in multiple ways. So you can provide dimension of each of the step, or you can dimension the whole width and then dimension of 3 of the steps, right? Now which one is correct one? Each way of dimensioning is going to drive different kind of variation into the assembly. So tolerance stack-up analysis can help us determine that. Tolerance stack-up analysis will tell us which is the optimal way of dimensioning it and tolerancing this part. Should the drawing be redimensioned or retoleranced to reduce the accumulation of tolerances? What is the accumulation of tolerances? If I have to calculate the total tolerance of this width, it will be the accumulation of all the tolerances of each of this width. So if I have to reduce the accumulation of tolerancing, I can think of, is there any better way of dimensioning the part, or is there any better way of tolerancing the part? Have I optimized my tolerancing to meet the same function? And these answers are going to help us to reduce the overall cost by reducing total variation into the system. Have we evaluated product change requests more objectively? What does it mean? Suppose you get a request of change. So you release a design, drawing and CAD model, but now a quality engineer came to you and he is asking for the change in the tolerance value. So initial tolerance value was 10 plus minus 0.25, and then he is asking you to change this tolerance value to plus minus 0.7. Now how you will decide whether you are going to do this change or not, right? So for that, if you already have tolerance stack-up analysis, you can very easily plug in this new tolerance instead of old tolerance and check the impact on your function and result of the stack-up. If it is still meeting the function, then it is opportunity for you to accommodate this change into your drawing. So these are some of the top advantages of stack-up analysis. There are hundreds of them, but at least now you got the idea of why tolerance stack-up analysis is so crucial. Now let's understand what are the different types of tolerance stack-up analysis. So the first type is linear versus radial. So wherever there are radial dimensions involved or diameters are involved into your stack-up analysis, that is called as a radial tolerance stack-up analysis. Whereas where non-diametrical parts and their dimensions are involved, then we call it as a linear stack-up analysis. Then we also have a type manual and computer assisted. Most of the cases you can solve with the manual stack up analysis or with the help of Excel sheet. But there are certain cases in which dimension is going to vary in three directions. That is going to affect our function. In such cases, we have to go for computer assisted tolerance stack up analysis, because normal stack up analysis, manual stack up analysis cannot determine. For example, we have a cross section like this, and there is a part which rotates in this, right? Something like this, and it can rotate, and all three dimensional variation in these two parts is going to affect how freely this part is going to rotate. In such cases, we cannot use one dimension analysis. So for that, we need softwares like CTOL, which is going to help us for this 3D analysis. But here is the good news. Most of the stack up analysis you can solve with the manual or Excel sheet, which is easy to calculate compared to the 3D analysis. Then we have part or assembly stack up, based upon whether we want to find out the gap or distance on the part or between two parts into the assembly. The next type is whether we have 1D, 2D or 3D tolerance stack up analysis. 1D means all the dimensions are going to be in the same direction. Okay, one direction only. All contributing dimensions are into one direction only. Here we are touching these two parts together on the inclined face. That means little bit of trigonometry is going to be required in order to convert this 2D analysis, because variation is going to happen in two directions, and we have to convert this 2D variation into 1D. If we can't convert that into 1D, then probably we have to go for 3D analysis of this. And 3D we already talked about this case, if you remember, right? So this case is all about 3D analysis, because here variation is going to happen in all three dimensions on all the directions, and such kind of analysis can be done only with the help of tools like CTOL. Then we have types of worst case or statistical. So what is worst case means? Worst case relies more on analysis with the worst case of each tolerance value. That means we are going to imagine that each contributor dimension is going to vary to the worst case, and what is the combined effect of that on the assembly level. Whereas statistical analysis works on the assumption that every dimension is going to vary statistically. And by statistically, what do we mean? Every dimension is going to follow normal distribution, or every dimension is going to follow little bit skewed normal distribution, right? Based upon that, we have these two methods. We have RSS method, root sum square method, which assumes this one, and we have modified root sum square methods which assume this one. Now worst case and RSS method, they are two extreme ends, and MRSS falls in between them. Then we have tolerance stack up using coordinate tolerancing system or geometric controls. Every GD&T symbol with every modifier has a different meaning, right? So how to tackle that into our stack up analysis? That is whole big topic altogether. So based upon whether we are using coordinate system or geometric tolerance system, the interpretation part might be changing a bit. Now here I am going to explain one basic example just to give you idea of how tolerance stack up analysis works. So we have the part and we have all the dimensions, and what we want to find out is what is the maximum and minimum width of this group. Now why we want to find out? Because we want to place one spacer here in this group, okay, and we want to make sure that the spacer is fitting into this group when these all dimensions vary, and then we get maximum and minimum width of the group. So you might be thinking why this dimension is not given, then directly we can give the dimension, right? But this part is a legacy part. Legacy part means this was an old part which was used in other design. Now we want to use the same part for our new design. So this spacer was not there into old design. This is only added into new design, and that's why we have to find out this gap, right? If this is a new drawing, definitely we can add directly this dimension. But because we have legacy case here, that's why we have to check whether this part is fitting or not. So spacer dimension is given. It is 5 plus minus 0.8. That means it can vary within upper specification limit of 5.8, which is 5 plus 0.8, and lower specification limit of 5 minus 0.8, which is 4.2. So these are upper specification limit and lower specification limit which we have to meet. Now in order to do stack up analysis, first we have to find out the starting point, and at the starting point is generally to the left, that is the convention. You can take it at right also, not a problem, but when we have consistency in assigning the start point, then we get the consistent results and sign conventions. So that's why most of the times we use left to right and bottom to up. So here left side we are going to use as a start phase, the right side towards end is positive, that means end is B, right? If the A is start, B is end. So we have positive, and then in opposite side we have negative. So that is the convention we have to follow when we find out the chain. Now the second thing we have to do is find out the chain. Now what is chain? Chain means it is the shortest chain from the start point towards the end point. This chain will be the chain of dimensions. Now what is the criteria? In chain, the criteria is when our first dimension end, the second dimension should start exactly from that point, and it should create the shorter distance. Now let's find out how we can create the shorter distance, shorter chain here. So our first dimension is going to start from the start point itself, because this is the start point, right? So we are going to start from here and we have to reach here. There is no direct dimension here, so we have to find out which is the shorter chain. So the first dimension is going to be how much? 30 plus minus 0.2. So that is going to be our first dimension here, and this is first dimension. Is it positive or negative? So we have to look at the convention. So you see here convention right to left is negative, left to right is positive. Here we are going to the left, and that's why this dimension will be negative. Then we reach to this phase. From this phase we have to reach to this phase. So now I can go here also, or I can go here also. So which dimension I have to select? So I have to find the shortest way. So obviously the shortest way is this one, right? So now I reach to this phase. From this phase I will directly move to the right side. So my dimension is moving towards right. This is my second dimension, and this dimension is moving towards right. That means as per convention it is positive, right? And now I reach to this phase. So from this phase I have to reach to the end of this. So this is going to the left. So this dimension is third dimension, and it, as per sign convention, right to left is negative. So that's how I got three contributors in my chain, and this is the shortest distance I traveled from this point to this point. Now if you observe here, one dimension ends, second dimension starts exactly from that point, surface or line. That is very important to understand. Now let's put these all things into a stack up form. So in stack up form, first dimension is what? First dimension is 30 plus minus 0.2, and it is negative, so I have to put it under negative. So 30, and then I have to put tolerance, which is plus minus tolerance, right? So here we have plus minus tolerance of 0.2. Now the second dimension is what? 45 plus minus 0.2, which is positive. So 45 will come under positive, and what is the tolerance here? Tolerance is 0.2, right? Then third dimension is 10 plus minus 0.2, it is negative, so I'm going to put it 10 plus minus 0.2. okay. Now we are going to take summation of all the positives, summation of all the negatives, and summation of all the tolerances. So what is the summation of all the positive? There is only one dimension there in positive, so which is 45. Then what is the summation of all negative? 40. So which is nothing but our summation of negative. And what is the summation of all the tolerances? 0.2 plus 0.2 plus 0.2, which is nothing but 0.6. So we got a system level tolerance which is 0.6. So we can directly copy it here, which is system level tolerance. This is the total variation going to happen into our system. Then what is the mean? Mean is the difference between summation of positive and summation of negative. So 45 minus 40, which is nothing but 5, is the mean. And this mean and this tolerance are going to give us maximum and minimum limits. So 5 plus 0.6 is going to give us maximum limit. So which is nothing but 5.6. And then 5 minus 0.6, which is going to give us 4.4, right? Which is going to give us 4.4. Now we can easily compare that with the result. Hopefully by this time at least you have got the idea of how tolerance stack-up analysis looks like and what is the use of stack-up analysis and how stack-up analysis is going to be helpful in your design.